Hello, everyone. Hope you're all doing well. So this will be the only day that we're meeting today. Make sure that you take your test. If you haven't taken it yet, you have until tonight at midnight. There was a homework assignment that was originally due yesterday, but it got pushed back till next Sunday. So if you're like, oh crap, I missed the homework last night, you actually didn't miss the homework last night. So you got a little extra time. We're going to finish up that chapter hopefully today. So let's take a peek here. All right, so chapter 11. Thus far, we've talked about just alkanes. So for our hydrocarbons, hydrogen and carbon mixed together, we've been looking at alkanes, ANE, meaning that all the carbons are single bonded to each other. Sometimes they're called saturated hydrocarbons because they have the maximum number of hydrogens you could fill it. Now we're going to move into unsaturated hydrocarbons, which there's two different types. There's alkenes and there's alkynes. This is ethine right here. This is carbon and it's triple bonded to carbon. It has a common name as well, but I wouldn't expect you to know common names. So alkenes and alkynes are a family of hydrocarbons that contain, if it's an alkene with an ENE ending, that'll be a double bond. So it'll be a carbon double bonded to another carbon. The double bond is not carbon to hydrogen. It's not a carbon to oxygen. It has to be a carbon double bonded to one of the other carbons on the main chain. If there happens to be a triple bond, we'll call it an alkyne with a YNE to the end of it. And again, these are called unsaturated hydrocarbons. They're unsaturated because one of the spots that could have been filled with one of those hydrogens has now bonded with the carbon, right? So we've kind of stolen one of the hydrogen slots and made it a double bond. These alkenes and alkynes will react with hydrogen gas to increase the number of hydrogens. So we could take something that's unsaturated, like for instance, this here, and we could pump hydrogen into it and we could actually saturate it. So we could break some of these bonds and then plug hydrogens on there. You can't do that with an alkane because it's already saturated. So let's start with alkenes. They contain one or more carbon-carbon double bond. This is ethene. We have carbon double bonded to another carbon. Remember, ETH means that we have a chain of two carbons. So 2 carbons, and those 2 carbons happen to be double bonded to each other. Look what happened to the number of hydrogens here. Okay, if we are looking at ethane, which you should be comfortable with already, that would be carbon bonded to carbon single bond, and we would have a hydrogen, a hydrogen, a hydrogen, and then hydrogens over here, okay? So this would be F-A-N-E. If I say ethene or E-T-H-E-N-E, what I'm denoting is that there is a double bond here. So what happens is this hydrogen goes away, this hydrogen goes away, and what would normally have been the bonds to the hydrogen now becomes a double bond there, all right? So only 2 hydrogens when we change it to an ene. 2 hydrogens here, 2 hydrogens here. When filling in the hydrogens, you know, again, just always make your original chain and then just figure out how many open slots it has. So this carbon has 1, 2 here, so it only has 2 open slots for hydrogen. This carbon has double bond here, so it only has 2 open slots. Bond angle for this would be 120 degrees as opposed to the ethane. So if those hydrogens were there, let's put them back in there. There are 4 groups. Let's get rid of that. It'd be 1, 2, 3, 4 groups. That'd be 109. Here, though, we only have 3 groups, right? 1, 2, 3 around this carbon. So it would be 120 degrees or trigonal planar as opposed to tetrahedral. Hold on one second. Yes. teaching, honey? You want to say hi? This is my mini me. Okay, I gotta teach. Can you close my door? All right, so alkynes are, they'll end with a YNE. And so if we've got ethine here, this is where we have a carbon triple bonded to another carbon. I don't know if they give us the drawing. They don't. All right, well, we'll just draw it up here. So it would be carbon triple bonded to another carbon. Now look, this carbon only has room for how many hydrogens? Just one hydrogen, right? Because it's got 3 filled slots here and it only gets 4. So this one can have 1 hydrogen and this one can also only have 1 hydrogen. So in this instance, around this carbon and also around this carbon, look, there's 1 group, 2 groups. So this will be 180 degrees, or it'll have a linear structure. So the carbon in the ine group will have a linear, the carbon in the ene group, ENE, will have 3 groups or 120 trigonal planar. And then if it's in ane, it'll be tetrahedral. So for this, we're just going to identify the following compounds as either an alkene or an alkyne. So with this first one here, and I know these structures sometimes look really scary because there's nothing there, right? But there are things there. Remember, the ends and the points are carbons. The lines represent bonds. And here we can see that there are actually 2 lines. So this is acting as a double bond. All right, this is a carbon and this is a carbon. So we have a double bond between 2 carbons. So that would make this an alkene. We won't name it just yet. This one here, there's a carbon here. I know this is a straight line, but we can assume that there's a carbon right here where those other 2 end. So this is a triple bond. Triple, and what does triple give us? Triple is an al, YNE, alkyne. So an alkene and an alkyne. This is kind of where we start to talk about this thing called priority. And certain things are more important than other things, okay? So that double bond and triple bond are more important than like having the longest chain. So if you could technically make a longer chain this way, we wouldn't count that and say, oh, it's an alkene or an alkane. We would want to go with whatever had the triple or the double bond. That's kind of more important. So as far as naming is concerned, you'll name the longest carbon chain that contains the double or the triple bond. So if you can make a longer chain with only singles, doesn't matter. It's got to have the double or the triple in it. Number the carbon chain starting from the end nearest the double or the triple bond. So again, if you have accessories, let's say you've got a fluorine and a methyl group, those are not as important as the double or triple bond. So the double and the triple bond take priority. So we'll always number those the lowest. Give the location and name any of the substituents in alphabetical order as a prefix to the alkene or the alkyne. So if we're looking at this guy here, we want to figure out our longest chain. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Doesn't matter. So I'm going to go this way. 1, 2, 3, 4, 5. Now I want to number them so that my double bond starts towards the lowest number. So 1, 2 would put the double bond at 2. If I went the other way, 1, 2, 3, it would put it at 3. So we're going to count this as 1. This is 2, 3, 4, 5. And you may be saying, well, but if we counted it this way, then the methyl group here would be at a lower number. Remember, that is a lower priority. The double bond is always the higher priority. So 1, 2, 3, 4, 5 for our main chain. So what is the prefix for 5? Pent. And then because there's a double bond in it, we're going to it. Now we have to say where that double bond is, because the double bond could have been here. It could have been here. So you've got to let the reader know, hey, this double bond is happening, or it's starting on the second carbon. So I'm going to call this 2-pentene. Remember, dashes go between numbers and names. So 2-pentene denotes that the double bond is on the second to the third carbon. Then if we have any accessories, we need to add those in. So the only accessory I can see here is this methyl group. And the methyl is happening on the fourth carbon. So we would go 4-methyl-2-pentene. Looking at this one here, I can see that this is an alkyne because I've got a triple bond. There's only really one chain. So we've got a carbon here, 1, 2, 3, 4, 5, 6. So 6 is hex. The double bond means that it's going to be ENE, hexene. We have to say where the double bond is, because the double bond could have been over here. It could have been in the middle. It could have been on the end. I don't want to count this as 1, 2, 3, 4, 5, 6, because it would put this on the fourth. I'm going to start here and make this 1, 2, 3, 4, 5, 6. So it will be on the second. So this will be 2-hexene. We got a question here. I did E, didn't I? Didn't I? Look how confident I was there. Guys, bring me back down. All right. So yeah, Yne, Y-N-E, because it's a triple bond, which I said it is in fact a triple bond, and apparently. So not hexene, hexyne. I'm sorry about that. So this guy would be 1, 2, 3, 4, 5, 6, 2, YNE. Let's see, I think that's probably, it's a triple bond. Yes, it is. It is. So we've got our 2-hexyne, our 2-pentene, and then they add the 4-methyl in there. There are no substituents. There's no accessories on this one. So this is a relatively simple one. What if we have a cycloalkene? So we can have a situation where we have a cyclical and there's a double bond on it. Well, anytime you have a ring structure and you have a double bond, you're always going to start the number 1 where the double bond is. Okay, so looking at this structure, this is going to be 0.1. It's just how it goes. This has a higher priority than the methyl group. So we wouldn't start 1 here and then count out to the double. We would start at the double. So this will be 1, 2, and 3. Because you always assume that the double bond is happening at carbon 1, like this, we don't have to say that it's 1 cyclopentene. This is 5 carbons, 1, 2, 3, 4, 5. In a circle, that's where the cyclopentene is coming from. We don't need to say it's 1 cyclopentene though, because we just assume it's on there. Now we have to add accessories. So if we stopped right here and just looked at cyclopentene, that would be this structure minus this accessory here, right? It'd be like if we didn't have this thing, but we do have an accessory. So we have to add what this thing is, which is a methyl, and it's on the 3rd carbon. 1, 2, 3. Could you have counted in the other direction? 1, 2, 3, 4. That would have put it on the 4th. So we don't want to count in that direction. We want to count in the direction that's going to make it the lowest number again. So I want you to name the following alkenes or alkynes. So try it out. You've got two here. They're both cyclo, so you better have the word cyclo in both of them. All right, so looking at this one, we have a double bond here, and we want to count how many carbons in total we have. So 1, 2, 3, 4, 5, 6 carbons. So 6 carbons is going to be hex. There is a double bond there, so I do need to put an ENE, hexene, and it's cyclo. So it's making a circle. I don't have to say it's one cyclo. We're just going to assume that, this is carbon 1. There aren't any accessories on there, so we can just leave it as cyclohexene. This one over here, 1, 2, 3, 4, 5 carbons, so it's pent. Double bond, so that's going to be the ENE, and it's in a circle, so cyclo. Now I don't have to say that it's on carbon 1. We're just going to assume that it's carbon 1, and I'm going to put, this is carbon 1, this is carbon 2, this is 3, 4, 5. You may be wondering, well, could we make this carbon 1 and then this carbon 2? No, the carbon 1 is where the bond starts. All right, so the double bond will always be between, when you have this cyclo, it'll be between 1 and 2. I wouldn't want to count this way because it would be 1, 2, 3, 4. This would be putting it on the 5 for the accessories. So this will be 1, 2, 3, and then we've got 2 methyl groups. Right, this arm here is a CH3 at the end of this, CH3. So we call those methyl groups. There's 2 of them, so it's got to be dimethyl. We can smush that against the cyclopentene. And they're both on 3. So it's going to be 3,3-dimethyl cyclopentene. Oh my goodness, what a mouthful. One thing I do want to talk about when we're looking at this is just like how many hydrogens are there, okay? Because if I was to fill this in with hydrogens, this is not a saturated hydrocarbon. In a saturated cyclical hydrocarbon, every carbon would have how many hydrogens? It would have 2, right? Because this carbon is attached to a carbon here and a carbon here, so he has room for H and H, right? 1, 2, 3, 4, that fills the 4. This guy here has access to, can have access to 2 hydrogens. This guy can have access to 2 hydrogens. What about what's happening with this carbon though? This carbon has 1, 2, 3 of his slots filled. So he only has 1 open slot. So he just gets 1 hydrogen. Same thing with this one over here. This carbon has 1 buddy here and 2 bonding buddies here for a total of 3. He only has open room for 1 hydrogen. What about this one? This one is also a hydrogen and a hydrogen. So just because the hydrogens aren't drawn in on a structure like this, you would need to be able to know how many there are, where they are. Let's look at this one here. This one has 1, 2, 3, so it can have 1 hydrogen. This one here has 1, 2, 3. This can have 1 hydrogen. This guy here, 1, 2, so he can have 2 hydrogens. Same thing with this one, 2 hydrogens. What about this carbon right here? Right there, he has 1, 2, 3, 4 buddies. So he doesn't have any hydrogens on him. Okay. What about this carbon here and this carbon here? Well, those are methyl groups, right? So it's bonded by 1. So it has a hydrogen, and a hydrogen. Same thing with this one. It has 3 hydrogens. Any questions on like how you can get the number of hydrogens? Every carbon wants to have 4 connections. So you make the structure and then see what's left over, and those get filled with hydrogens. All right, so when we're looking at things that have double bonds, remember how I said with single bonds that the structure could rotate around itself and it was completely fine? So single bonds, you can rotate. Double bonds and triple bonds, you do not have the freedom to rotate around a structure. So I'm gonna go back to, go over here for a sec and just draw. So we'll look at 1-chloroethane. So carbon bonded, single bonded to carbon, and it's got a hydrogen, a chlorine, hydrogen. Okay. So if this is a single bond, we say that this is the same as if I was to draw it like this. Carbon, chlorine, hydrogen, carbon. Okay, so do you see how on this one, the chlorines are on the same side? And on this one, the chlorines are on opposite side? All this thing did was to get from here to here was this sort of rotated, right at this bond. That you can do with single bonds. So this thing and this thing are in fact the same if they're single bonded. Now I'm going to draw something a little different. Carbon double bonded to carbon, and I have a chlorine, a hydrogen, and a hydrogen, versus carbon double bonded to carbon, and I've got a chlorine, hydrogen. These are not the same. Why? Because this thing does not have the freedom to rotate. So if the chlorines are on the same side, that is different than if the chlorines are on the opposite side, if there is this double bond. This double bond or triple bond sort of freezes it in space. This single bond allows rotation. So let's look at how you would name these things. This here is known as a cis structure, CIS, on the same side. When you have the thumbs on the opposite side, so if we've rotated it 180, that would be known as a trans structure. So looking at this thing here, if I was to draw this structure here, 1,2-dichloroethene, which is, I believe, what I had on the whiteboard. You have to ask yourself, is this the cis or is it the trans? You can't see it when it's drawn like this. If it was drawn like this, or if it was drawn like this, you would be able to denote whether it's cis or trans. So on this side, same cis. Opposite will be trans. This shape will hold, all right? So the chlorines will always stay on the same side because you can't rotate to form this. Again, same thing with this. These opposite formations will stay sort of rigid or frozen. They won't rotate to form this. And this is important to know if something is a cis or a trans, because just having the chlorine, it's like, well, it has the same formula and it has almost the same structure. That little adjustment can have huge effects. So in a cis isomer, the alkyl groups are attached on the same side. So here's butene. And butene, we've got a double bond. So we've got 4 carbons, 1, 2, 3, 4. The double bond is in the middle, and we can see that the little methyl accessory groups are pointing in the same direction. This would be known as a cis. Trans 2-butene is where you have this step stool. And again, remember, that wouldn't matter if this was a single bond. But because this is a double bond, this doesn't have the freedom to rotate around. So lots of pheromones and things like that have these cis-trans effects. Here's a silkworm. It's like sex pheromone. Okay, it's like a cis and a trans structure. We don't need to get into the details of that. But let's look at this thing here. So if I was to look at this structure, this one over here would be cis, the cis version. So it's both of these are 1,2-dibromoethene. But so 2 carbons, 2 bromines. But in this case, the bromines are pointing in the same direction. So we give it the cis. On this side, it's trans because the bromines are on opposite directions. Do remember when you're looking at this structure, where are the carbons? There's a carbon here, and there's a carbon here. There is not a carbon here, okay? This line encompasses the bromine, right? Same thing with this one. So sometimes it'll look like, oh, there's 1, 2, 3, 4 carbons. There's not here. There's 1 here and 1 here. When you have the bromine written, we attach the line with it. Okay, so this is only a 2 carbon situation. All right, so looking at these here, I want you to name each one, and I want you to say whether it's cis or trans. So give me the full name too. I want you to go through and name the thing. Figure out what the longest carbon chain is, figure out if there's a double bond. There is in every one. Add accessories if need be. And then tell me if it's cis or trans. All right, so gone are the days of just flip-flopping charges to get to get your name, right? So we've got to find our longest carbon chains. All of these have a carbon chain of 1, 2, 3, 4, right? 1, 2, 3, 4, 1, 2, 3, 4. So they're very similar. So they're all bute. They have a double bond, so it's butene. And if you notice, every single one has a double bond on which carbon? On the second carbon. Okay, so whether you count it from this way or this way, it's on the second carbon. So they're all two butenes. This guy down here doesn't have any accessories, right? He's just got the double bond and then hydrogens. So he's going to have the simplest name. It's not enough to say he's 2-butene. We've got to say, hey, are those things popping up or is it popping down? Now, again, you wouldn't be able to do that if the structure wasn't drawn like visually to see it this way. So because these groups here are opposite of each other, we're going to say that that's trans. Looking at this one, we do have accessories. All right, so we've got a bromine and a bromine, and they're both on carbon 2 and carbon 3. So we need to say dibromo, 2 bromines. They're on 2, 3. And then we have to add whether it's cis or trans. In this case, they're trans. The bromines are on opposite sides. Looking at this one here, we've got the 1, 2, 3, 4. So we've got the butene. The double bond is on the 2. And then we've got 2 accessories, a chlorine and a chlorine. 2 chlorines are going to give us dichloro. It's on carbon 2 and carbon 3, and they're both popping out on the same side. So we would say that this is cis. So this one here, cis 2, 3, dichloro 2 butene. Does it get more complicated? Oh, it so gets more complicated. But we don't get much more complicated than this. We'll do some more accessories, but just know if you're going into an organics class, if you have to take a full organics class, I don't know if any of you will, it does get more complicated than this. So you do need to know a couple things about reactions, specifically addition reactions. So there's I got a question here. Where did the 2-butene come from? Okay, Janine, so let's go back and look at that. So why are we saying 2-butene for every single one? So I'm gonna cut this right here. So the 2 that comes directly in front of this is telling me where the double bond is, right? The but tells me the number of carbons. The ene tells me that it's a double bond somewhere in that chain. The 2 tells me where the double bond is. Because you could have a double bond here, right? Or you could have one there and one there. So you've got to let the reader know where that double bond is when the chain is longer than 3. Right? If it's 1, well, you wouldn't have a double bond with 1. You wouldn't, if you have a double bond with 2 carbons, you know exactly where it is between carbon 1 and carbon 2. If you have 3 carbon chain, you would know where it is because you could just flip the structure. Once it gets to 4 or more carbons, you got to let the reader know. So that's the 2. All right, so if you've ever heard of hydrogenated oils, that is this process right here. This is where you convert a double bond that's in like a vegetable oil to a single bonded carbon chain, or you saturate the fat. Have you heard of saturated fats and unsaturated fats? Okay. So going through this process of, we've got a couple different things that we're going to talk about, but hydrogenation, and then we've also got hydration. That's a little bit different. So hydrogenation is when we take an alkene, and it can be any alkene. So anything that has a double bond between 2 carbons. We pump hydrogen into it. We then throw some sort of catalyst in there. Usually it's platinum or nickel. And what will happen is that double bond, and I'll show you guys, but the double bond will open up and it will accept hydrogens to make it an alkane. So it will no longer have the double bond, it'll have a saturated structure. So let's look at this. I've got, this is what, ethene. So we've got a carbon double bonded to another carbon. Each carbon has 2 hydrogens. We would say that this is an unsaturated carbon. Why is it unsaturated? Because it's got the double bond. It doesn't have as many hydrogens as it could potentially have. So what we do is we pump a bunch of hydrogen gas into it and we run it over platinum. And this double bond will open up and receive 2 hydrogens. So this carbon is sharing this double bond and this carbon is sharing this double bond. So if I get rid of this, what does that leave? Well, now this carbon is short a slot, right? He has 2 here and he has 1 here. He needs another thing. So it'll open up and we'll stick a hydrogen on it. If that one does it, this one also needs to do it. So we get this as our end structure. So our alkene, ene just meaning a double bond, turns into an alkane, ane, or a single bond. The same thing can happen with an alkyne. We can take something that has a triple bond and we can open up 2 of those bonds to receive 4 hydrogens and we can saturate the structure. In this case, we would need 2 hydrogens. Here we only needed 1 hydrogen diatomic molecule because right, this hydrogen is really 2 hydrogens, 1 here, 1 here. Here we've got to double it up so that we can fill in 4 open slots. If I come around here and if I get rid of this bond and then I also get rid of this bond, right? This carbon has 2 open slots and so does this one. And we'll pack it in. So I want you to write an equation for the hydrogenation of 1-butene using a platinum catalyst. So first write your 1-butene, add hydrogen, draw an arrow and put platinum over it, and then tell me what the result would be. Try it out. It's going to look very similar to this, but we don't have 2 carbons. We have 4 carbons. If you're like, I have no idea, just try it. See what happens. Just try it. We'll go over it in a second. Okay, so if you get the basic idea of what's happening, you draw your structure, you open up the double bond and you shove hydrogens onto it. It doesn't really matter how long the chain is, right? Everything else is kind of not important. It's only really what's happening at the double bond that's important. So let's first draw our 1-butene. So if it's 1-butene, that means that we have a carbon and it's double bonded to a carbon and then single to carbon and single to carbon, right? This has hydrogens all around it. This thing has 2 hydrogens. This thing has 1 hydrogen, 1, 2, 3, and 4. And this thing has 2 hydrogens. Okay, I don't care about the cis and the trans here. We're just drawing this basic structure. So here is really what we're looking at. This stuff doesn't fully matter. So if we're going through hydrogenation, that means that we're adding hydrogens. So I'm going to add 2 hydrogens because this is just a double bond. The ENE lets me know it's a double bond. And then I'm going to run it. It says over platinum, so PT. It'll just sit over the arrow. So what we do is we open this up and we shove the hydrogens on it. So it becomes carbon single bonded, right? We lost that double bond and we fill it in with hydrogens. The only real difference here in this structure is right here, right? So this hydrogen and this hydrogen are new. They came from what used to be that double bond there. That makes sense? What if I said something like the hydrogenation of 2, nonene, 9 carbons? It wouldn't be any different. You'd just have to write out 9 carbons, but it's really only at the double bond that we're seeing any effects. So there we go. We've got our double bond and it opens up. It becomes, here it's unsaturated. Here we have now a saturated hydrocarbon. So hydrogenated oils is when we add H2 to the double bonds of vegetable oils. Why do we do this? This creates compounds with higher melting points. They tend to be solid at room temperature, such as margarine, soft margarine, or shortening. So it makes these things more solid. Also creates a higher melting point, so they're better to cook with, so they won't burn. All right, so I want you to write the product for these 2 things. This one's a little different, but just try it out, all right? Figure out how many hydrogens everything has, break the bond, shove some hydrogens into it. All right, so with this one, this is 2-butene, a little different than the last one, still 4 carbons, but this is where we're gonna look at the change. So that double bond will erase itself and it'll open up 2 open spots where we'll put the hydrogen in. Okay, so now we have a saturated situation. This one might have been a little bit trickier for you. This had 1 hydrogen coming off of it, and this had 1 hydrogen coming off of it, all right? These all had 2 hydrogens. I'm not going to draw them all in, but what we do is we get rid of this, bye-bye, and we can put another hydrogen in it. Did it draw that here? No, it's just assuming that you know that if there's a carbon at each of these points, they each have 2 connections, so they'll have 2 openings for 2 hydrogens. There's another reaction that you do need to know, and that's a hydration reaction. So it sounds really close to hydrogenation. Hydrogenation is hydrogen. Hydration, like you can think of the word hydrate, water, okay? In this situation, we're gonna take an alkene, so something that has a double bond, and we're gonna add water. But we're gonna write water like this. We're gonna write it as an H bonded to an OH. The reason that we're going to write it that way is so that you can kind of mentally separate a hydrogen from an OH. So in this case, we have our carbon double bonded to another carbon. That bond is going to open up. But instead of just receiving hydrogen and hydrogen, one of them is going to receive hydrogen and the other one is going to receive an OH. Usually this one is done in an acidic solution. That's what the H plus is for. And we'll get something that looks like this. This thing over here, this OH, is an alcohol group. And we will talk more about alcohols in the next chapter. For now, though, just if you see an OH on something, it means it's an alcohol. So if this is the generic, right? How long this carbon chain could be, as long as you want, right? Or as long as the problem gives it to you. But the important thing is that in a hydration situation, the double bond opens up, one gets an H, one gets an OH. So our alkene turns into what we call an alcohol. So if we do this for ethene, which is just 2 carbons, we open up the double bond, we shove a hydrogen on one, we shove an OH on the other, and that makes this thing called ethanol. And I don't expect you to be able to name those just yet. We'll name those in the next chapter. So looking at this top one here, predict the product of the addition of HOH, which again, this is just referring to H2O. They've just sort of written it out so that you can see that you've got one thing here and one thing here for the following alkenes. So looking at this structure, this is where we expect to see the change. Everything else is going to stay the same. So I've got a carbon with 3 hydrogens, a carbon with 2 hydrogens, a carbon that initially had 1 hydrogen, right? It was double bonded to another carbon that had 1 hydrogen, but I'm going to make it a single bond. And then I'm going to add the rest. What else do we have? We have a carbon with 3 hydrogens, okay? This is the magic area. When I open that bond, I now have 2 open spots. One of them is going to get an H, one of them's going to get an OH. Looking at this one here, the difference is that this one had the double bond somewhere in the center of the chain. This one has the double bond at the end. The process is the same though. I've got CH3, CH2, carbon here is originally just bonded to 1 hydrogen, and then it's bonded to this other carbon, and this carbon had 2 hydrogens. I'm going to open up that double bond. So there's 2 open slots, and I'm going to put a hydrogen and an OH there. All right, so we open this thing up and we stick that on. For this one, it looks like they put the OH here instead of at the end. I'm not gonna be a super stickler about where you put the OH and the H just yet. Okay, the last thing, I think this is the last thing in this chapter, are these things called aromatic compounds. So an aromatic compound contains this structure right here, which is known as a benzene ring. A benzene ring is 6 carbons and they have alternating double bonds. So you can see there's a double bond here, there's a double bond here, and there's a double bond here. So with that, every carbon has one hydrogen around it. So the structure, the molecular formula for this is C6H6. This is so common, this benzene ring is so common that it gets its own name, right? Benzene. We don't call this, hexene 135 hexene. We just call it a benzene ring. Michael Faraday discovered this. He was a super smart dude, did a lot of crazy stuff. So benzene is an aromatic compound. We're going to have 6 carbon atoms, each bonded to 1 hydrogen, and then there is going to be alternating double bonds. Sometimes this is written with the double bonds. Here we can see there's one here, and one here. Or they could alternate. So they could sort of, this double bond here maybe moves here. And if it moves there, then this one is going to move here, and then this one is going to move here. All right. And then like we're here, and this one's going to move here, and this one's going to move here, and this one's going to move. So they kind of rotate. But that doesn't mean that there's 6 of them. There's only ever 3 double bonds, but they kind of oscillate around. So it is common to see this structure written like this with a circle in the center. So if you're seeing this structure, this is benzene. It means that there are 6 carbons, there are 3 double bonds, and they're sort of rotating around in the structure. Very, very, very common formula. So common that we even have names for the benzene rings that have these accessories. So if you have what you would name as methylbenzene, so we've got a benzene ring with a methyl group off of it. This is actually has a common name called toluene, and we see it quite often. Here's another, this is an aminobenzene, so this is an amine group, aniline. This one you do need to know the name for, and we will come back to it when we talk about alcohols. But when you have a benzene ring that has an OH group off of it, we call it phenol. And I don't want you to call it hydroxyl benzene. I want you to be able to call it phenol. Okay, but we will revisit that. So when there are 2 or more constituents on a benzene ring, go ahead and number them so that you can give it the numbers to the lowest constituents. So we don't want, so looking at this one, this is a benzene ring. I don't want to put 1 here, right? 1 is always going to be at wherever the substituent is. And I don't have to call it 1-chlorobenzene. I can just call it chlorobenzene. There's a chlorine attached to a benzene ring. This one has 2 chlorines. So I'm going to give one of the chlorines number 1. So this will be 1, and 2, 1,2-dichlorobenzene. Benzene ring encompasses this. Over here, I've got chlorine on 1 here, and then we'll put this as 3. I wouldn't want to count in the other direction because it would go 1, 2, 3, 4, 5. I'd rather have a 1 and a 3. So 1,3-dichlorobenzene. This one is 1,4-dichlorobenzene. All contain a benzene ring, all have accessories. You can also use the common names, toluene, phenol, and aniline, to name these things. So like looking at this one here, I can call this aniline, which is a benzene ring with this NH2 group on it. I don't have to call it aminobenzene. I can just sort of use the aniline name to encompass this thing and the ring. This will always be on the 1. So then it'll be 3-bromo plus whatever this is. This is a phenol right here. So we'll call this whole thing phenol. We don't need to denote that the HO is on the 1. We assume it's on the 1. What else do we have? Well, we've got a chlorine, so 2-chloro. We've got a bromine, so the 4-bromo. Why do we put the bromo before the chlorine? If it's a bigger number, we do that because of alphabetical order. So 4-bromo takes this, the 2-chloro takes this, and then the phenol encompasses the rest of it. Oh, look at this mess. Okay, we've got a methyl group attached to a benzene. We call that toluene. So toluene takes up, I'm looking at the name here. Toluene is talking about all of this. Then we add the accessories. We've got this and this and this. The bromine, so it looks like it doesn't really matter which direction we go, it's symmetrical. So 1, 2, so we've got a bromine on the 2 and the 6, so 2,6-dibromo. We've got a chlorine on the 4, 4-chloro, and then toluene is including this thing as well. Here's TNT. So we've got 2, 4, 6 trinitrotoluene. That's where that name comes from. So remember, toluene is the benzene ring with the methyl group. And then these, I wouldn't expect you to know this, but these are called nitro groups. There's 3 of them. So that's where the trinitro comes from. Trinitrotoluene, TNT. Okay. There's another one down here. So, okay, so let's look at these guys. Let me erase that. So let's go ahead and name these things. So this here has a chlorine group on it and a benzene ring. So benzene and the chlorine, there's only one accessory here, so we just assume that's on one. We don't need to say that it's on one. So this would be chlorobenzene. You don't need to call it, well, you definitely don't call it cyclohexene. What would chlorocyclohexene would look like this. Pen, stop disappearing on me. Sorry, that's a really cruddy drawing, but hopefully you can get the idea. There's no circle in the center, okay? If there's no circle in the center, these are all single bonds. Here, remember, we've got that double bond that's oscillating around. So we don't want to call it cyclohexene. We don't need to denote that it's on the 1, so we would just call this chlorobenzene. This guy here, we could call it toluene, but they're not calling it toluene because they're not expecting you to know the everyday names. So we've got a methyl group and a methyl group. This is carbon 1, 2, 3 to keep the numbers low. So 1, 2, 3, 1, 3, 1, 3, dimethyl, and then benzene encompasses the ring. Okay, isn't that so much fun? So you do have a lab where you get a lot of practice with all these. 11:59. What time does this class get out? 12. Okay, I'm going to give you some to name. I'm going to mix a bunch of things together. So I'm going to give you the names, and I want you to draw the structures. And then we'll do some going in the other direction. Okay, 3,4-dichloro-1-octene. And you draw that. One, two. It's hard for me to make these up out of thin air. 1, 2, dimethyl. And we'll ditch the 4. Okay, so 1,2-dimethyl cyclopentane. And I'll give you one more. Okay, so for this first one, when I'm working on these, I kind of like to work from right to left, which is a little weird because we read it left to right, but I would start with your chain. So this says we've got octene, so we have 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. And there's a double bond, and the double bond is on carbon 1. God, the end of that looks horrible. Let's make that look a little better. Okay. So the double bond is on carbon 1, 1 to 2. So I'm going to put that right here. Now remember, this takes precedence. So this is 1, this is 2, this is 3. And we do have some accessories, 2 chlorines on group 3. So I'm going to put a line and connect it to a chlorine. And then on 4 as well. Put another one here. 1,2-dimethyl cyclopentane. So start from this direction. Pentane means that I've got 5 carbons. They're all single bonded, and cyclo means that they're in a circle. So it'll look like a little house. All right, 5 points. On carbon 1 and carbon 2, we have 2 methyl groups. So I'm going to put a line and a line. This one, 3-chloral, 1-fluorobenzene. So we have a benzene ring and then we have to fill it in with a circle. On one, we have fluorine. So fluorine. On a 3, so 1, 2, 3, we have chlorine, Cl. If you would put your Cl over here, that would be fine. If you put your F here and your Cl here, that would be fine. I could rotate it around and know what you were doing. Questions on those? Let me do a couple. I'll give you the drawing and I want you to tell me what the name of it is. Ugh. I'll give you a couple minutes for those. Okay, I'm going to move through these just for sake of time. So hopefully you at least got them drawn. So looking at this first one, I'm going to find the longest chain that has any sort of double or triple bond. So 1, 2, 3, 4, 5. 5. 1, 2, 3, 4, 5. Yeah. So pent. And there is a double bond. So pentene. Now I have to specify where that double bond is. I don't want to start my carbon counting here. I want to start it here. So this is 1, 2, 3, 4, 5. So the double bond starts on the 2. So it's 2-pentene. Then I have to add any accessories. I have 2 bromines. So we've got a dibromo. And those are on 2 and 4. So 2, 4 dash dibromo 2-pentene. This one here is a circle or cyclical. There are 6 carbons, 1, 2, 3, 4, 5, 6. So they're all single bonded. So that's hexane. If I started this as carbon 1, that would be on a 1, 2, on a 1, a 3, and a 4. If I start this as 1, I'll have it on a 1, a 2, and a 4. Those are lower numbers. So I'm going to start this as carbon 1, 2, 3, 4. I'm going to list the chlorine first because it comes before methyls. These are methyl groups in alphabetical order. So I've got a 4-chloro. Dash, sorry, it's going to get a little smushed here. One, erase this. Dash 1, 2, dimethyl hexane. This is covering this. This is covering these. And this covers the final ring. This one here, this is just phenol. Okay, benzene ring with an OH off of it. This one here, 1, 2, 3, 4. I've got, so that's bute. There's a double bond, so it's butene. The double bond is on the second, so 2-butene. And because of the structure of this, they're both pointing up. I can actually say that this is the way it's drawn. I can say it's cis-2-butene. If it happened to have looked like this would be the trans. This mess here, yes, cyclohexane. Oh my goodness. Oh my goodness. Cyclo. Can you tell I'm already on vacation? Cyclo. Thank you. Thank you. Janine, you were going to ask the same thing. Yes. Always ask. If you think I'm wrong, I'm probably wrong. So tell me. So let's go with 4-chloro-1,2-dimethyl cyclohexane. Last one here, 1, 2, 3, 4, 5, 6, 7. So that's hept. And there is a double bond, so E-N-E. The double bond is on the first carbon, so 1 heptene. And then we've got a bunch of methyls. So this is 1, 2, 3, 4, 5. We've got 2, 4, 5 dash trimethyl methyl dash. Just make some more space here. Come back to me. All right, 2, 4, 5. Dash trimethyl dash 1 dash heptene. This covers the double bond. This covers the carbon chain. This lets us know where the double bond is. And these are the accessories. Okay, so we are going to leave it at that. I will not see you all until next Monday. We're not meeting on Wednesday, so have a good holiday. Stay safe out there. Eat a bunch of food. Just eat a bunch of food, as much as you can. And stay around if you have any questions. Otherwise, I'll see you guys later. Bye.